Good morning, students. Today we will be studying about Module 1, that is all about discrete Fourier transform. To begin with, let's start with a brief introduction. Generally, for the analysis of digital signals, we generally prefer to do it in frequency domain. That is what I meant to say. Frequency analysis is usually performed and it's more conveniently chosen to analyze a given discrete time signal using DSP, digital signal processor. Obviously, as we know, all signals are available to us in time domain. There is a need for us to translate from time domain to frequency domain. For that, the tool which we'll be employing is what is called as Fourier transform. By subjecting x of n to Fourier transformation, the resulting function, what we get is the frequency spectrum x of omega. But if you could observe the spectrum x of omega, it's found that x of omega is said to be continuous with respect to omega. So as long as x of omega is said to be continuous, it's not all that convenient for the hardware to effectively represent the given discrete time signal x of n. So what we need to do? We are required to discretize that frequency spectrum x of omega. That is why we are required to do what is called as sampling operation to so obtain frequency spectrum x of omega. That is the topic to be followed in the next session. Okay, what is called as frequency domain sampling. Whatever discrete time signal we had got x of n has been subjected to Fourier transform to get the frequency spectrum x of omega. Since x of omega is continuous in nature, we will be discretizing x of omega to collect the samples at regular intervals of time or at equal intervals of time. How exactly we do the sampling in frequency domain will be discussed in the next topic. To begin with, what is the first step? I've got a discrete time signal x of n. What is the nature of the signal? It is aperiodic in nature and it is said to be an energy signal comprising of finite energy. By subjecting x of n to Fourier transform, I get the frequency spectrum x of omega using this basic formula. As I showed you earlier, if you could plot the spectrum x of omega with respect to omega, this is how the spectrum looks like, which is said to be continuous in nature. But please note that even though it is continuous in nature, it is observed that the spectrum x of omega is periodic with a period 2 pi. That is, for an every interval of 2 pi, the spectrum is said to repeat itself. Hence, it is said to be continuous and periodic with period 2 pi. Now, as I said earlier, what I must do, what exactly we are doing here? We are trying to obtain the samples of the spectrum x of omega. So now we have to decide upon the sampling interval. That is why I assume that x of omega is said to be sampled at equally spaced intervals delta of omega. What is the value of delta of omega? We'll look at it sometime afterwards. And we do the sampling operation assuming that there are capital N, equidistant samples between the interval 0 to 2 pi. Okay, the total number of samples in the interval 0 to 2 pi is capital N. And since we have observed that x of omega is continuous, and as well as periodic in nature, it is just sufficient if you could consider the spectrum over one interval, that is the range of omega lying between 0 to 2 pi. As I told you, whatever is the spacing between any two consecutive samples, that is delta omega, is given by 2 pi divided by n. 2 pi refers to the finite range, the finite value of omega, okay, and n refers to the total number of samples present within the range 0 to 2 pi. After subjecting to what is called as sampling operation, the above, this is the equation. This equation gets converted to this particular equation. What you can observe is when you could compare the two equations, the place of omega is taken by this variable 2 pi by n times k. Here also the value of omega is replaced by 2 pi by n times k. If you could ask what is k, k is basically the indexing of the sample where it can range from 0 to n minus 1. As I told you earlier, since the spectrum is continuous in nature, the spectrum is said to be existing anywhere from minus infinity to plus infinity. That is why the above summation can be split into what? Infinite number of summations. But keep in mind, if you could consider any one such summation, the total number of samples contained in any such one such summation will have totally capital N terms. So as an example, I've considered three different samples here, ranging from minus n to minus 1, 0 to n minus 1, n to 2n minus 1. In each of these three summations, if you could calculate, okay, by subtracting the upper limit from the lower limit, minus 1, minus of minus n in this case, n minus 1, minus 0 in this case. Similarly, in the third one, you can come to a conclusion that the number of samples present in each summation is equal to n minus 1, n minus 1. That is why the above equation can be summarized, or can be generalized, that's a better word, generalized into the above formula. Okay, where I'm introducing a new summation tag called as L, said to be varying from minus to plus infinity. This summation indicates that there are infinite number of summations present in the spectrum. We're trying to introduce a new variable called as P using this particular equation. While considering the second summation, okay, if I want to represent the second summation in terms of the new variable P, I'll consider the old limits and find out the new limits for P. Accordingly, using a simple mathematics concept, the new value of P turns out to be ranging from 0 to n minus 1. Along with the value of n is being replaced by p plus ln over here. Similarly, the value of n is being replaced as p plus ln over here. I've split the two exponential terms. Now, in the second exponential term, this term n gets cancelled. As I've discussed in the previous class, if you could expand the value of e to the power of minus j 2 pi kl by Euler's formula, it gets reduced to equal to 1. Sine 2 pi is 0, cos 2 pi is equal to 1. Accordingly, the formula turns out to be this. Please note that over here, what we have done in the next step is that I've tried to put the like terms under one bracket. Summation containing p, its corresponding exponential term over here, summation consisting of L and its corresponding term. And by mathematics, please note that since the value of L is varying from minus to plus infinity, x of p plus ln is also equal to x of p minus ln. because since L is varying from minus to plus infinity, the same values exist in both the cases. For the sake of our convenience, we are replacing x of p plus ln by x of p minus ln. Now again, to get the derivation, the formula in the standard format, I'm replacing the variable small p by n. And the above formula gets changed to summation n varying from 0 to n minus 1, summation L varying from minus to plus infinity, x of n minus ln exponential of minus j 2 pi by n times k. And here I introduce a new variable to be represented for the square bracket term. That new variable is being called as xp of n. What is xp of n? Given by this particular formula. What exactly xp of n denotes is, it is nothing but the periodic repetition of x of n. It's found that x of n is said to repeat itself periodically for every interval of n samples. That periodic repetition of x of n is represented as xp of n. I've shown examples for three examples for L is 0, 1 and 2. In each of these three cases, you can see that the same signal x of n is getting repeated itself for every interval of n, 2n, 3n and so on. That is why xp of n is said to be periodic in nature. Since the given time signal is periodic in nature, we can use the Fourier series representation. Accordingly, xp of n is represented by this particular formula using the Fourier series expansion. What is C of k? C of k is the Fourier series coefficient given by this particular formula. If I could compare the equation B with equation A, x of 2 pi by n times k is equal to what? Summation n varying from 0 to n minus 1, xp of n exponential minus j 2 pi by n times nk. This term will get replaced in the equation for B. I'm sorry. So this whole term will get replaced by what? X of 2 pi k by n from the result of equation A. Accordingly, the equation for Ck turns out to be equal to 1 divided by n times capital X times 2 pi k by n. And if you could, in the next case, once I know the value of C of k, I substitute this value of C of k in the equation for xp of n. I've got the equation for xp of n. In this equation for xp of n, I substitute the value of C of k. Accordingly, the equation for the periodic extension of x of n is what is called as xp of n, turns out to be 1 by n followed by this particular term. So what I do is I stop this video at this junction. The later part of it will be continued in the second video. Okay, so kindly check on to the next video for the continuation of this derivation.